So here Lagrange's theorem in abstract algebra. The statement of the theorem is if G is a finite group and H is a subgroup of G, then prove that order of H divides order of G. So in this theorem, G is a finite group. That means the number of elements present in the G are finite. So let us suppose that let order of G is equal to n. That means we are assuming that G containing n elements. H is a subgroup, that means H is also finite. Therefore, let us suppose that the order of H is equal to m. No doubt m is less than n or equal to n. So now our claim is to show that, I will write here claim, what we want to prove that in this theorem. So it is claim is to show that order of H divides order of G. That means that is to show that the order of H is m, therefore m divides n. Right? Now, what G is a subgroup? So, since G is a subgroup, there are two possibilities. Either H is a proper subgroup of G or H is improper subgroup of G. So what is the meaning of improper subgroup? Because G is a group and therefore default singleton E is always a subgroup of G. That means for every group we must say that there are always two subgroups should be there. One is singleton E and another is the group itself. So singleton E and the group itself are always a subgroup of given group, and these two subgroups are called as improper subgroups. So in the first case, if H is improper subgroup of G, then H is either singleton E or H equal to G. Therefore, order of H is equal to 1. If H equal to singleton E, then order of H is 1, or order of H is equal to n. And in both the cases, if order of H is 1 or order of H is n, both the numbers 1 is always divides n and n is always divides n. Therefore, when H is an improper subgroup of G, then this 1 divides n and n divides n. Hence, theorem for improper subgroup has proved. Now what happens when H is not improper? That means now I am considering the case if H is a proper subgroup of G. So that we want to show that when H is a proper subgroup of G, then also it divides. So H is a proper subgroup of G. That means definitely the order of H, that is we have considered, that is M, must be less than N. And now in this case we have to show that M divides N. Okay. Now let us consider one element from group. Let A1 belongs to G. So G containing n number of elements, and I am taking one of them and denoted by A1. So now I will construct a right coset of H in G using this element A1. So therefore H A1 is right coset of H in G. Now the question is, if H containing m elements, then how many elements are present in this right coset HA1? So H is a group. So instead of taking A1 element, we can take identity element, because identity is present in the group. So suppose instead of A1, if I'll take identity element from G, then HE, that is equal to H, and this is also a right coset. So this is a right coset, and we know that H containing m elements, and therefore HE, this right coset containing m elements. Therefore elements in HE are m. We have studied one theorem, that is, there is a one-to-one correspondence between any two right cosets of H in G. The meaning of this theorem is every right coset of H in G containing same number of elements, and hence if HE containing m elements, that means any right coset of H in G containing m elements, and therefore the cardinality of this right coset HA1 is equal to m. Right? Okay, the next thing is, let us suppose that there are k which is less than m, which is less than n. Let us suppose that there are k distinct right cosets of H in G. So let us consider what are these k right cosets. So let HA1, this is the first right coset, HA2 be the second, and in this fashion the last one is HAK. So these are the, let HA1, HA2, HAK be distinct right cosets of H in G. We know that the distinct right cosets of H and G creates equivalence class for every element A1, A2, AK, and therefore we can say that every distinct right coset partition of G, and therefore G can be written as union of these right cosets. So HA1 union HA2 union, and the last is union of HAK. Now what are the elements? That means we are taking order of G. So therefore order of G is equal to order, or we can say cardinality, number of elements in HA1 plus number of elements of HA2 plus the last one is the number of elements present in the last right coset, that is HAK. We know that the order of G is equal to n, and we have shown that the number of elements present in the right cosets are m. So it is m plus m k times. If any element added k times, then it can be written as k into m, and hence n upon m is equal to k, where k is integer. We know that the result from the number theory, if any number divided by another number, and if we are getting integer as an answer, then this m divides n, and hence we can conclude that m divides n, that is order of h divides order of g. And this is the end of proof of Lagrange's theorem.